If you're on campus, I hope you're staying inside. I haven't seen any text saying that they've got the suspects apprehended or anything. So check your email, make sure you stay safe. Let's do some calculus. Oh my goodness, this assignment. So at the end of the semester, I always, because my brain's frazzled, right? And I start doing the homework ahead of time, like the examples. I don't just walk in, hey, let's do some calculus and see how it happens. And it's a good thing, because one of these problems, no lie, took me 30, maybe 40 minutes to do, and it drove me nuts. And I almost decided just to let you guys do it on your own. But I'm not that big a jerk. So I left it in, but I'm pretty sure problems like this are not going to show up on the exam. Let's take a look. Excuse me. It's all good. Yeah, it's not COVID. It's a different C word. And I don't have a cold. All right, so November 18th, 2021. Today, 5.9 is the last section we're going to talk about, differentiation and integration of hyperbolic functions. Now, this is probably the first time that everybody's kind of on the same page. My guess is none of you have really seen hyperbolic functions before today, and I got to make that go away because I keep looking at myself. I don't know why. I hate it. It's just the way it goes. Hyperbolic functions are completely new. So what is a hyperbolic function? It's when we look at a unit circle, right, for sine and cosine, and it makes a circle. Well, excuse me, I'm so sorry. When we put some exponential functions together, so now we're looking at our transcendental functions, and put these together and we create hyperbolic functions. So we have this equation, and make sure I get it right. Let's draw for a circle, and our regular trig functions, sine squared x plus cosine squared x equals 1. But for the hyperbola, we'll have hyperbolic cosine squared of x minus hyperbolic sine squared of x equals 1. So this one little change, but order matters, right, in subtraction. I should have written those in the other order. Order matters in subtraction, and so this little minus sign changes everything. Sine and cosine are no longer determined by a unit circle. In the hyperbolic world, it's determined by e to the x and combinations, e to the x and e to the negative x. We frequently call this one sinh. Actually, if you're spelling it correctly, if you've ever ridden a horse, it's like cinch, like you cinch the saddle tight, all right, sinh and cosh. The other one we call hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, and a hyperbolic cotangent. We don't use those as often. So these ones have quick and easy words because mathematicians could say sinh or hyperbolic sine. And you know we lazy, so I'm going to be saying sinh. With the definitions, right, here's our identities. Oh, look at that. I didn't even have to write it there. It's right here. So we have the basic definition. We have how tangent and secant are related hyperbolic world, and how cotangent and cosecant are related in the hyperbolic world. We have a square formula, a double angle formula, some sum and difference formulas, cosine squared, and double angle formula cosine, hyperbolic cosine. So those formulas are there. I've actually made it, and I put the skeleton notes up. Hopefully I updated the skeleton notes correctly. Page 1 and page 5 are full of formulas. I think it's 5, it might be 3. Page 1, definitely print this out. It's going to be super helpful for you on the quizzes, quiz 12, and on exam 3. We're going to need this note page for like 1, maybe 2 problems. So we're going to work with hyperbolic trig functions. here we go. So if we want to evaluate the function, and I'm looking on my calculator because, you know, anytime I have to evaluate, my calculator is the first thing I want to use. And I don't have hyperbolic trig functions because they're not on calculator. So I have to get clever. And we see that the cosecant, hyperbolic cosecant of natural log of 2 is what? Hyperbolic cosecant right here is the reciprocal of hyperbolic sine. Duh, okay. What is hyperbolic sine? E to the x minus e to the negative x over 2. So I'm going to put over here. Hyperbolic sine is e to the x minus e to the negative x over 2. Let me make sure I got that minus sign right. Hyperbolic sine has the minus. And cosecant, hyperbolic cosecant of x is 1 over sinh of x, which tells me, right, since it's the reciprocal, it's going to be 2 divided by e to the power minus e to the negative power. And our power in this case, x, is replaced by natural log of 2. So I'm going to put natural log of 2 here. And so to evaluate it, what we're really looking at is this. Check it out. 2 in the numerator. E to the natural log of 2. Remember, e and natural log are inverse operations, so that'll be 2. We're going to use this little skill we have right here frequently today. Remember that the negative sign can come up as an exponent, right? The power rule of logarithms come up as an exponent. If I have 2 to the negative 1, that's the reciprocal. So that's natural log of 1/2. So the negative natural log of 2 is the same as the natural log of 1/2. And e to the natural log of 1/2 will give us 1/2. Okay, now we need to do this. 2 minus 1/2, that's 1.5. This becomes 2 divided by 3/2, which equals 2 times 2/3, which is 4/3. I'm going to put this in a little box as an aside, and this is our answer. And for people not watching the video, that's kind of going to suck because that's ugly if you just try to read it off the paper. Okay. Oh yeah, that's why I didn't want to do that. We don't have another person yet. That's all right. All right. We'll collapse it. Collapse it. All right. Now let's do hyperbolic cotangent. Now we know what it's going to tell us. It's going to tell us that cotangent, hyperbolic cotangent, is 1 over tangent. But it's also going to tell us something super helpful, like the hyperbolic tangent is hyperbolic sine of x over hyperbolic cosine of x. I hate that the h is at the end because it's hyperbolic cosine. It seems like it should be hc. And that's not helpful until we also know that the hyperbolic cosine is e to the x plus e to the negative x over 2. And finally, in this unhelpful world of definitions of hyperbolic trig functions, right? They only give us 2 definitions. Everything else is built as we expect from the regular trig functions. We can now find the cotangent of natural log of 5. So I'm going to write it as cotangent of x, and then I'll replace natural log of 5 at the end. So the cotangent of x, a hyperbolic cotangent of x, is the reciprocal of tangent. So I'm going to do cosine divided by sine, and that one's over here still. Notice the only difference is sine is negative, cosine is positive. The other 3 parts are exactly the same. Sine is negative, cosine is positive. So as we all know, these 2's cancel out. All right, 2's cancel out, and we'll get e to the x plus e to the negative x over e to the x minus e to the negative x. But when x equals natural log of 5, this becomes e to the natural log of 5 plus e to the negative natural log of 5 divided by e to the natural log of 5 minus e to the minus natural log of 5. So I'm going to bring it down here a little bit. The natural log of 5, e to the power of natural log of 5 is going to be 5. For the same reason that negative natural log of 2 is equal to the natural log of 1/2, negative natural log of 5 will be equal to 1/5. In the denominator, we have exactly the same thing, but let me get my signs correct. 5 is 5 over 1. Denominator of 5 makes this 25 over 5, so this is 26 over 5. 25 minus 1 is 24 over 5, and we get 26 over 24. Cut each of these in half, and we're looking at 13/12. So evaluating hyperbolic trig functions comes down to evaluating exponential functions. Yeah. Isn't this fun? All right. And if you look at the notes that I posted for you guys, I think my notes kind of suck. But okay, I don't think they suck. I know they suck. They're horrible. I link you to some PowerPoint or something strange like that. This is going to be way more valuable for you than the lecture notes that I posted. I need to redo this section on my videos. Okay, so we know this. We know that the hyperbolic cosine squared of x minus the hyperbolic sine squared of x equals 1. And we know the hyperbolic sine of x is 3/2. So we can find this using the formula. So let's do that. My apologies. I forgot to turn off my ringer because I'm not on campus, but all good now. I'm going to call this W. What is the hyperbolic cosine squared? Minus 3/2 squared equals 1. W minus 9/4 equals 1. W equals 1 plus 9/4. And of course, that is 4/4 plus 9/4, which equals 13/4. But remember, this is cosine squared, right? So let me just call that W squared. What are we looking for? If what squared equals 13/4, then what will be the square root of 13/4, which is the square root of 13 over 2. All right. But now, as we saw in the last problem, when we're looking at cotangent and all of those things, actually, you know what I want to do? Let's do this for right now. I'm sorry. Bad scroll. Let me just hold this in place as we swing down here. There we go. Oh, that's not even the formula I needed. All right, so finding hyperbolic cosine, no problem, because we just do some algebra, just like we did with the unit circle. Now we're doing it with the unit hyperbola. All right, hyperbolic functions give us hyperbolic trig functions. A circle, I guess, not actually a function. A circle will give us our standard trig functions. But how do I get the hyperbolic tangent? I'm going to take sine divided by cosine. So I'm going to do 3/2 divided by square root of 13 over 2, which is 3 divided by square root of 13, which is a fine answer. But if you wanted to rationalize, that would be your answer. I'm of course too lazy to type that many characters when this is fewer. Let me bring it over here. Hyperbolic cosecant. Oh, but remember, cosecant is the reciprocal of sine. That's going to be our easiest one. That's 2/3. Do not miss this one. This is don't miss that. Like, you got that. If you miss the rest of them, we'll deal with it. Don't miss that one. Hyperbolic secant. Hyperbolic secant here is the reciprocal cosine. And that's another reason I like to leave, my radicals like this, because why not just flip it over? If you wanted to, you could rationalize your denominator. And hyperbolic tangent, oh, now this is where I wanted to tell you, if I leave it in this form and I flip it over, so we know that these two are connected. And we know that, let's get a different color, green. These two are connected, cosine and secant. And of course, our hyperbolic sine and our hyperbolic cosecant are closely related in that they are reciprocals. All right. Questions. Not fun, but certainly doable. Kind of taking you back to pre-cal. Oh, the nightmares. It gets better. These aren't even the hard ones yet. All right, I'm going to slowly scroll. We good? All right. So let's get into things that seem easier, and that's called calculus. So now what I'm going to do is I'm going to quick scroll. I want these derivatives. So I'm going to take these derivatives for now, just in case we need them. Let's see. I want the derivative of the natural log of hyperbolic sine. So I know that for the natural log, the derivative is derivative of inside divided by the original inside. So I know that the derivative is going to have a sinh or hyperbolic sine of x in the denominator. But then I ask myself, what is the derivative of hyperbolic sine? And I'll bring up my little cheat sheet here. My hyperbolic sine has a derivative of hyperbolic cosine. Right? Of course, times the derivative of the inside if it's not just a straight up x. But notice here with our formulas, sinh has derivative cosh. Cosh has derivative sinh. They just go back and forward. Notice there are no negatives in this. Hyperbolic tangent has derivative hyperbolic secant squared, which is just like regular trig functions. It's only the reciprocals in this case that have the negatives. It's not just the co-functions. So it's slightly different than the original trig in terms of positive and negative sign, but very similar in terms of what the derivatives actually are. So when we're looking for the derivative of hyperbolic sine, it happens to be just hyperbolic cosine. And we look at this and we realize, hey, that is just hyperbolic cotangent. There is a specific set of, you don't select cotangent and then throw in an H. There's a specific button for this on WebAssign. So make sure you use the hyperbolic trig functions. All right. Find an equation to the tangent line of the graph. I'm going to bring this up a little bit, hit save. Don't want to lose the notes we already have. And we're going to need some space. Find an equation of the tangent line to the graph of the function at the point 1, 1. We've been doing this since chapter 2. Like, we've been doing this a while. Equation of the tangent line. So we know that y prime is the slope of the tangent line. And we'll have y minus 1 equals the slope times x minus 1. So we know that we're getting this eventually. But when I look at this function, I think to myself, but then I notice, hey, the x is a base, and so our variable is both the base and the exponent. Anytime this happens, we go to my absolute favorite, logarithmic differentiation. So, and that's not even lying. I love logarithmic differentiation. So we're going to slam a logarithm in front of each of these. The reason for that is so that we can bring down that cosh x as a coefficient, right? It's the same rule we use to transform negative natural log of 2 into natural log of 1/2. The power rule of logarithms, that power comes down in front. Now we can take the derivative because we don't have any like crazy exponents or anything. The derivative of natural log of y is 1 over y times dy dx. The derivative of, product rule, right? We're multiplying, so it's first. Hyperbolic cosine of x, first derivative of the second, 1 over x, plus second, natural log of x, times the derivative of hyperbolic cosine, which we remember is the hyperbolic sine. And we really want to know what dy dx is, and we want to evaluate it at the point 1, 1. And since I know the y value, here's what I'm going to do. I'm going to take this whole thing and write it in a more compact form. So I'm going to take cosh x divided by x, add to that, there's no way of making this better, natural log of x times hyperbolic sine of x, and I'm going to multiply that all by y, right? Multiply by y on both sides to get the dy dx by itself. But when I put 1 in, I end up with hyperbolic cosine of 1 divided by 1 plus the natural log of 1 times the hyperbolic sine of 1 all times 1. And that's a lot of ones, but it's kind of nice that x and y are both 1. It makes it a little bit easier to evaluate. Hyperbolic cosine of 1 divided by 1 is hyperbolic cosine of 1. Natural log of 1 is 0. Natural log of 1 equals 0, so this whole thing is 0. And when I multiply by 1, we're done. That's it. So this is our slope, m. So going up here, we now have y minus 1 equals hyperbolic cosine of 1 times x minus 1. Y minus 1 equals hyperbolic cosine of 1 times x minus hyperbolic cosine of 1. If I want y by itself, I will have a large thing here instead of what I'm about to write. Hyperbolic cosine of 1 x minus hyperbolic cosine of 1. Take this 1 to the other side, and I have my answer. What is hyperbolic cosine of 1? It's e to the 1 plus e to the negative 1 all over 2, whatever that number is. We don't care. We want exact values, so we don't have to plug it into the exponentials and find out. We can represent it. We can represent it with the name hyperbolic cosine of 1. That's our slope. Totally unsatisfactory to people that like answers like 2.49. But it is what it is. How are we doing? I'm gonna let you write it down if you need to. I don't like going too fast. All right, fantastic. Appreciate the feedback. And I'm keeping this up here so I can keep an eye on the chat just in case. I suck at keeping an eye on the chat. That's what I need a TA for. All right, slow scroll. Here we go. Okay, so we're going to take derivatives. Great. But now we're also going to take integrals. So let's not. Well, let's look at it. Okay, so we could find the antiderivative of cosine because the hyperbolic cosine, I got to say the word hyperbolic all the time so you don't forget the H in your homework. It makes sense, right? It's just the opposite of what our derivatives are. Everything's backwards. I see no quotients here. There is nothing quotient-y at all. So as I'm looking at this problem, I'm going to stop scrolling back now. Don't worry, that's the last scroll back. As we're looking at this problem, we ask ourselves, all right, how do we approach it? But if we don't have quotient rule, right, and we don't have anything in our list of easy integrals, then we go to substitution. And when it goes to substitution, we look for an inside. There's not one. We look for something that's raised to a power. There's not one. Let's let u be that denominator then. We learned how to deal with denominators. We know that the derivative of hyperbolic cosine is hyperbolic sine dx. So when we're looking at our integral in quotient form, we can pull that apart so that it looks like 1 over hyperbolic cosine of x times hyperbolic sine of x dx. Right? If we can see exactly where our du is and where our 1 over u is. Because we know that the antiderivative of 1 over u is the natural log of the absolute value of u plus c, don't forget the capital C. When we reverse our substitution, this will be the natural log of the absolute value of hyperbolic cosine of x plus c. And that one was really straightforward, actually. I'm not saying easy, but in terms of, how things go, it's straightforward. Can you believe we're doing things like that? Go back to the August, and we're talking about limits. What happens when x gets close to a number? And now we're talking about these hyperbolic sine and cosine functions. Mind blowing. Okay. This one, number 10. Number 10 almost had, oh my goodness, like you guys. It's not that hard, but my brain was not having it. So I'm gonna trade pages. It's actually for me written out. I'm gonna show you this. I'm gonna see if you can see this. In my writing, that's number 10, half a page in my tiny itty bitty writing. So if I need to slow down, give me a thumbs down to slow down or something as we get going. Okay. Here we go. First thing I see is we don't have a product rule, right? E to the negative x, this whole 10, whatever, 10 comes out in front. We can ignore the 10 for now. But what I don't have is a product rule. I can't multiply. Just like in the earlier one, I had no quotient rule, so I had to do something. And when I have to do something, the hardest part is figuring out what it is I need to do. It turns out we're going to use this identity. Hyperbolic cosine in its basic form is e to the x plus e to the negative x over 2. And my hint for that is the fact that I have an e to the negative x here. Like, okay, if this is going to be exponential, let's rewrite using an identity. We do that all the time. Let's rewrite hyperbolic cosine in terms of e to the x's. So now if we have e to the negative x times hyperbolic cosine of x, this will be e to the negative x times e to the x plus e to the negative x all over 2, which is e to the negative x, e to the x, plus e to the negative x, e to the negative x, all divided by 2. Oh my goodness, I'm so glad I don't have to caption this myself. That's got to be miserable. And I wrote it this step that most of us don't need, but remember, when you're multiplying two things with the same base, you add their exponents. Negative x plus x is 0, and e to the 0 is 1. E to the negative x and e to the negative x makes e to the negative 2x, all divided by 2. And I want to remind you, this is 1/2 plus e to the negative 2x over 2. So what we've done is we've rewritten our antiderivative. Yep, said that right. Instead of e to the negative x times hyperbolic cosine of x dx, I can now write this as something that looks a little easier. I'm going to call this a 1/2 e to the negative 2x instead of over 2. It just looks easier, taking those coefficients out instead of freaking out thinking you have a quotient is sometimes better. All right. Everything's in terms of x. We're good. I'm going to break this into 2 parts. We have 10 from 0 to 2 of 1/2 dx plus 10 integral from 0 to natural log of 2, 1/2 e to the negative 2x dx. Over here, we ask ourselves, what has derivative equal to 1/2? That's going to be a 1/2 x. So we'll have 10 times 1/2 x evaluated from 0 to natural log of 2. We'll come back to that. And then over here, I'm going to simplify this step. And I'm going to do some substitutions. Let's move on to another color. So here I'm going to let u be a negative 2x. Then du is negative 2dx, which means I have negative 1/2 du equals dx. So I got dx, I got u, so I brought the 1/2 out in front, times 5. So I have 5 e to the u times a negative 1/2 du. All right. Simple, not easy, simple substitution that we might have had in an earlier section. This would have been before the inverse trig stuff. All right, and we can do this. We're going to, oh, no, we're not finished yet, right? Because also, when x equals 0, u equals 0, but when x equals natural log of 2, u is negative 2 natural log of 2. But that actually happens to be 1/4. That's not true. It's natural log of 1/4. I'm going to leave it just like that. No, I'm not. I'm going to make it so other people can read it too and not just me. When x equals natural log of 2, u equals negative 2 natural log of 2. This way, I never have to go back to my x values. All right, but we're still working, right? We're working on 2 of these at the same time. We're almost out of paper. Hopefully that means we're almost done. So this is a 5x evaluated from 0 to natural log of 2. Remember, because we took care of that integral without substitution. So its limits didn't change. That's why I'm looking at these separately, so I don't get so confused. To that, we're going to subtract. Why subtract? Because of that 1/2 and that 5. Subtract 5/2. The integral of e to the u is e to the u. And that is evaluated from 0 to -2 natural log of 2. It's all right. We only need one more line. We're almost there. 2 more lines. So this 5x, when I put in 0, I'm just going to get 0. This is going to be 5 natural log of 2. 5/2 times e to the -2 natural log of 2 minus e to the 0, right? Minus 5/2, and then I evaluate top minus evaluate at the bottom. This is a 5 natural log of 2 minus 5/2. Now remember this -2 natural log of 2. We can bring that power back up. But 2 to the -2, that's 1 over 2 squared. That's the natural log of 1/4. So e to the natural log of 1/4 is 1/4. E to the 0 is 1. 1/4 minus 1, this is a 5 natural log of 2 minus 5/2 times a -3/4. That -5/2 times a -3/4 will be a positive 15/8. I'm going to put that right up here. 5 natural log of 2 plus 15/8. And if you look at it, I mean, come on, Tuesday, that wasn't really hard. Really? Yeah. The 10. The 10 and the halves and which half and this half and that happened. It got to me after a while. It's not as hard as it was for me this morning. But it definitely has a lot of steps. So I'm going to take a drink, take a breath, let you finish writing, and then we're going to go over it again. All right. So we can take the 10 out, take care of our constants first. Constants come out in front of the integration. So now we're looking at the function that we're trying to integrate. It's called the integrand, the function that's inside the integral. And e to the -x times hyperbolic cosine of x. I know what to do with an e. I have no idea what to do with the hyperbolic cosine. So how about we put that in terms of our e's, right? It's definition. And I can rewrite my integrand into something that's easier to deal with. First step. And that first step, super important. Always try to substitute out and make trig functions, whether they're hyperbolic or regular. Try to make them not so complicated, not so hard. And hyperbolic cosine, hyperbolic sine, hyperbolic any trig function, we're going to go to the e to the x plus e to the -x all over 2 definitions in order to make it happen. Algebra takes place. Over here in calculus. So since we have an addition here, we also have a rule that says the integral goes through sums and differences, just like the limit, the derivative, anti-derivative. We can split up sums and differences. So now this 10 integral and dx has to go with both of them. So 10 integral 1/2 dx plus 10 integral 1/2 e to the -2 dx. Right? They always have to come together. The 1/2 dx, we know what has a derivative of 1/2 x does. And we want to evaluate that from 0 to natural log of 2. And we kept our 10 out there. And I could have taken that 1/2 out earlier and called it a 5 here and then whatever. It all ends up the same. There's like 3 different ways you could get from this line to this one. So don't worry about whether your step was exactly like mine or not. Let's leave that here. We'll be back. Our second antiderivative. So we have the 10 still, and then we have the 1/2 e to the -2x dx. I could take that 1/2 out and get a 5. Definitely, because I have other stuff going on. It's my only number. I'm not too concerned about it. But if I have other stuff going on, I get my coefficients out of it. As I look at e to the negative 2x, I know that the antiderivative of e to the u is itself. So we have to deal with the du. So I let u be negative 2x. The derivative is negative 2 dx. We don't have a negative 2 hanging out. We had a half. We don't have a negative 2. So I divide to the other side. Negative 1/2 du is dx. So I can replace dx directly with my negative 1/2 du. I have e to the u, and my 10 times 1/2 is out in front. The only thing we haven't talked about are our limits, but when we change u from x to u, we have to change our limits from x to what u is. And we're going to simplify that second u here in a minute. All right, so I finally got this into a form that is negative 5/2 e to the u du, and we know that that antiderivative is itself. It's just e to the u. All right, so here we are, and now I'm evaluating 5x from natural log of 2 to 0. 5 natural log of 2 minus 5 times 0. I didn't write 5 times 0 because I evaluated how much space I had. Minus 5/2 times, now I'm going to evaluate e to the negative 2 natural log of 2 minus e to the 0. Negative 2 natural log of 2 is the natural log of 1/4, and e to the natural log, inverse operations, e to the natural log of 1/4 is 1/4. E to the 0 is 1. And algebra. Where did we do calculus? We did calculus a couple of steps here. This is actually a calculus-driven problem. All right, that's big. Are we good to move on? I just noticed the time. All right, I know you're still writing, you're still thinking, you're still trying to figure out how your constant, because that's the only thing that changes here, affects your problem. I get it, it's all right. But you see, there's also inverse hyperbolic functions there on page 5, so I would think about printing these as well. I don't expect to see these on the quiz or exam, but you never know. I haven't checked yet, that's why I don't know. Derivatives of hyperbolic functions, notice there's only 2 that are negative. The inverse hyperbolic tangent and inverse hyperbolic cotangent have the same derivative. Inverse hyperbolic sine and inverse hyperbolic cosine, they're only off by that sign right there in the middle, the plus or minus. Same thing for hyperbolic secant inverse and hyperbolic cosine inverse. Remember that in terms of reciprocals, these ones go together, right? In terms of reciprocals. So it's easy to keep the signs together because the plus in the hyperbolic cosecant goes with the plus in the hyperbolic sine, reciprocal action and everything. Notice once again, just like in inverse trig functions, standard trig functions, there are only 3 integration formulas. So we're going to do number 12, and then maybe we'll do number 14. Let's look at number 12. The derivative of a hyperbolic secant. All right, let's write this formula down. So I want the derivative hyperbolic secant, and we know that the derivative d dx hyperbolic secant inverse of u is minus u prime over u times the square root of 1 minus u squared. That's what my notes say. Let's check and make sure. Yep, we're good. Notice that this one has an absolute value, the cosecant, hyperbolic cosecant inverse, but the hyperbolic secant doesn't. Very subtle differences, but things we need to keep in mind. Okay, so hyperbolic secant has this derivative. So in this case, my u is sine of x. My u prime, just a straight up sine of x, not like hyperbolic or anything. We're going to go back and forth between the two. Yeah, that's not confusing at all. Yeah, good luck entering that on WebAssign. Woo! Go slow, right? You're doing this work for 5 or 10 minutes to do a single problem. Take more than 30 seconds to make sure what you typed in is what you actually wanted typed in. It's worth it instead of like, oh man, what did I do? Because that do a problem for 5 or 10 minutes and then that deflation of, oh, I got it wrong, you didn't get it wrong, you just typed it wrong. That hurts. Okay, so the derivative, hyperbolic secant inverse, is the derivative of the inside divided by the inside times 1 minus the inside squared. But that's not going to be a good answer. We're not going to do that because, check this out. We all know sine squared x, we started this lecture with this. Sine squared x plus cosine squared x equals 1. So this is cosine of x over sine of x. And I know you're thinking cotangent already, right? Better than that. 1 minus sine squared is cosine squared. Oh, but what's the square root of the cosine squared? That is, oh, what did I forget? I forgot my minus sign. Don't forget your minus sign. Minus cosine of x over sine of x, cosine of x, right? Square root of square. Oh, and between 0 and pi over 2, cosine of x is positive from 0 to pi over 2. So I don't have to have absolute values here. If it was all 0 to 2 pi, well, the cosine might change signs and I have to have an absolute value. But on this interval, I don't. And if I don't have to have absolute values, then these are the same. And my answer will then be -1 over sine of x, which we all know to be cosecant of x. Let's call that negative. So yeah, something horribly ugly. Y equals the inverse hyperbolic secant of the sine of x. Find the derivative. Boom, that's negative cosecant of x. It's no problem. Give me something real. Okay. How we doing? We're not good, Tuesday. All right, thank you, Hazel. Here's the deal. Class is over. If you need to leave, you can leave. But number 14 took a whole page of paper. So I'm going to do number 14 on video anyway. Hopefully this meeting doesn't shut off at 11:30. So we try to do it in 10 minutes. Stick around if you'd like. Otherwise, have a great day. I will see you by Zoom again on Monday at 10:30, but it's just office hours. I'll be available during class time for questions only. I will have nothing prepared. If you want to talk about your review, we'll talk about your review. I will not be recording anything next week because it is just drop-in questions. So that way, if I pull up yours, I don't have to worry about I'm recording your scores or anything like that. So next week is drop-in only via Zoom. I'll have links up again. Stick around if you want to, but it is 11:20. Class dismissed. Here we go, number 14. Nope. Let's just do what we know we need to do and put that on another sheet. Okay. Find the indefinite integral using the formulas from the theorem regarding differentiation and integration involving inverse hyperbolic functions. And I'm going to start with a hint because I needed it. And our hint is this. All right, finish stating. Make sure I have plenty of paper just in case. All right. We are going to let, okay, go blue. U be the square root of x. Then du is 1/2 x to the -1/2 dx. But we can write this better as du equals 1 over 2 square root of x dx. Or we could write this instead as du equals 1 over 2u dx. And finally, 2u du equals dx. All right, so I'm going to use u equals square root of x, and I'm going to use 2u du equals. I don't know what happened. It's like it went away. I don't know. We're still recording? Everything good? I don't know. It went away. I hope you're still here. For reals. Let's see. Let u be the square root of x, then du, we find the derivative. We rewrite it because rational exponents, whatever. Okay, I got that, but u is square root of x, so I can put u in there. So 2u du equals dx. Yeah, that's what I was afraid of. I really don't know if this is recording right now. How does this help? Now, the integral, 4 of square root of x divided by the square root of 1 plus x cubed dx equals let's go with also x equals u squared. All right, so the square root of x is u for integral. I don't know, that's a weird place for the 4. Not for the 4, for the u, I can't handle it. Underneath, in the denominator, we have the radical 1 plus, but instead of x cubed, x is u squared. So x cubed is u to the 6th. And in place of dx, we have 2u du. Man, mushmouth today. I'm going to move that 2 out in front also. We'll end up with an 8u squared over the square root of 1 plus u to the 6th du. All right, great. Now we need to do it again. Let's use green. Maybe it'll be good luck for the Seahawks. They need all the luck they can get. But you see, this isn't good enough. So we don't have a form that matches this. So we're going to do a second substitution. We're going to let b be u to the 3rd. Then dv is 3u squared du. I have a u squared, that's cool. So we have 1/3 dv equals u squared du. All right. So this one becomes, I still have my 8, my integral, this u squared du makes 1/3 dv. The denominator is now the square root of 1 plus v squared, and we can tighten that up a little bit. As 8/3 times the integral of 1 over 1 plus v squared dv. However, slow scroll. I'm going to capture this so we can look at it a little bit. Let's capture this right here. Antiderivatives of a form we've never seen before. Put it over here. Nope, let's put it over here. Sorry, we gotta go away. Put it over here. Now I'm looking at this form, and still to this day we have tables, and you're going to have a table available to you of these integrals. Notice that it's d whatever, u squared, variable squared plus a constant squared. In this case, right, the order of adding is different, but it's addition. And when it's addition, we don't care. Addition can go either order. So here my a squared equals 1, and we can see our v squared. So the antiderivative here is the natural log of the variable plus the square root of that inside. So this is 8/3 times the natural log of, in absolute values, the variable plus the square root of 1 plus b squared plus c. I'm going to check two places here. First of all, I'm going to bring this up so we can look at it. Make sure I did it correctly. Remember, if 1 is plus here, it stays plus. The signs go with each other, plus or minus in the correct order. Fantastic. That's exactly what I have on my notes, and I'm happy about that. But now I'm worried about this shutting off on me. So we're going to now reverse our substitution. We know exactly what v is. The natural log of v is u cubed plus the square root of 1 plus, if v is u cubed, that's u to the 6th. But we know exactly what u is also. U is the square root of x. U is the square root of x. So this is the square root of x to the 3rd plus the square root of 1 plus the square root of x to the 6th plus c, and we'll finish that with natural log of, in absolute values, x to the 3/2 plus the square root of 1 plus, the square root is the 1/2 power, 1/2 times 6 is 3. And that's our answer, and I'm really hoping that this recording is going to be good and not all weird, since it took us kind of out of it all. And that's my answer, and that's an actual true answer because I looked it up. And is it one of the ones I'm looking at? No. There we go. It's number 14. And you can see that the format, the only thing different is the 5. I had 4. So 5 times 2 makes there 10. I have 4 times 2 makes 8. But it is exactly in the right form. When we're adding, we don't care about the order. This problem, best of luck to you, number 17. Stop our share. I'm going to stop the recording.